definition. If K is a convex subset of vector space, then the point A in K is an extreme point of K if there is no open line segment that contains A and lies in K. So let ext K be the set of extreme points of K. So ext ext K is the notation for the set of extreme points of K. So recall that an open line segment is a set of the form x1, x2 equals the set of points 1 minus t x1 plus t x2, such that t is from 0 to 1. Z is greater than 0 but less than 1, where x1 is not equal to x2. So this is geometrically, this is a line segment. So if t is 0, look at this formula. Then here you get 0, here you get 1 times x1. So t is 0 corresponds to x1. T is equal to 1 corresponds to x2. But here, t is from 0 to 1, but 0, 1 not included. So the endpoints are not included. So that's why it is an open line segment. So here, in the definition of open line segment, x1 is not equal to x2. So if x1 equals x2, then this is just 1 point. For any t, this is just 1 point. So that is not open. So we exclude that situation. The book includes that, considers that as an open line segment also, and they use a different term. Now, what is the book you says that okay, the book uses a proper open line segment. By the book, proper means x1 is not equal to x2. So, but I think that this is more convenient to define this way. So the proper open line segment in the book is the same as our open line segment here. So by the definition, a point A in K is an extreme point if and only if no open line segment with endpoints in K minus A contains A. Thus, A is in X K if and only if each such line segment is contained, since it's in K but does not contain A, so it's contained in K minus A. So each such line segment is contained in K minus A. This just it is the same. This is saying that this set is convex. So therefore, a point A in K is an extreme point of K if and only if K minus A is convex. So now we have Klein-Millman theorem 7.4. If K is a non-empty compact convex subset of a locally convex space X, then K is equal to closed convex hull of Xk. Proof: we look for a maximal proper. Here the proper means unequal to K. Relatively open convex subset of K. This relatively open means open subset of K if we consider K as a topological space. So if a subset is contained in K, then when we say open, that is the same as relatively open. So here we emphasize that, say this is relatively open. So this means, this just say that it's open in K, but not open in the original space X. Okay, so from now on in the proof, relatively open is the same as open because we just consider subsets of K. So let U be the collection of proper. This is the same. Proper means unequal to K. Okay, we don't have to say it again, but proper just means unequal to K. All right. So relatively open convex subsets of K. Okay, we just U is the collection of such sets. Okay, just that this set have three conditions on these sets. One, it is proper. Set, it is open. Then it is convex. Okay, proper, open, convex subsets of K. Then U is non-empty, is not an empty set because U contains at least one element. It contains empty set. Okay, it contains an empty set. So here we, this U is a non-empty set. Then with the relation subset contained in, with this relation, U is a partially ordered set. The order is what? So when you have this relation, just means this relation means one set, one member is contained in the other member. Then the two elements, two members have this relation. This is a partial order because we could have two open sets. Neither one is contained in the other. So it is not true that every two elements can be compared. So it is a partially ordered set. Let U0 be a chain. Okay. Let U0 be a chain. So U0 is a chain. Chain means totally ordered subset. This means it is a subset of U. Subset, subcollection of U. Subset or subcollection of U. Such that every two members in U0 can be compared. So it is a totally ordered set. Okay, it is a totally ordered set contained in U. So this U0 is a chain. And we put U0, this big U0 equals the union of all U. U is a member of U0. So this U0 is the union of all members of U0. Okay. Clearly, U is open and convex. U is open and convex. If U0 equal to K, then the compactness of K implies that there is U in U0 with U equal to K. So by the compactness, since the union, this U equals, the union equals K, that means this U form a cover of K. But K is compact, so finitely many members, the union is K. But since this is a total ordered set, then for the finitely many members of U0, you have there's a largest one. So this largest one itself equals K. But then that's a contradiction because U is a proper subset of K. So this is a contradiction to the property of U. So therefore, this U0 is not equal to K. So U0 is proper. So you already know it is open, convex. Now it is proper. So U0 is a member of U. So this says that every totally ordered subset has an upper bound. So this U0 is an upper bound of the collection U0, okay? So this U0 is a member of U, which is an upper bound for the script U0. So by Zorn's lemma says that suppose a partially ordered set P has the property that every chain in P has an upper bound in P. Then the P contains at least one maximal element. So we have the above reasoning. This part of the reasoning shows that our collection, our partially ordered set U, script U, has this property. So by Zorn's lemma, U must contain a maximal element. So U has a maximal element, we call it U. Suppose that x is in U. X is a point in U. And lambda is a positive non-negative number less than 1. So we consider this map Tx lambda. This is from k to k, be defined by Tx lambda y is equal to 1 minus lambda x plus lambda y. This is the point at the lambda position of the segment from x to y. On the line segment from x, y, you take the lambda position, and this is the point. Okay, so this point must be in K because this is the line segment from X to Y, and the K is convex by the hypothesis. So this is from K to K. So then this is maps U to U again because U is convex, so it maps U to U. Since K is convex and hence connected, a convex set must be connected. Okay? Convex set must be connected. So K is connected. So a proper non-empty open subset of K cannot be closed. So a proper non-empty open subset of K cannot be closed. So if it is, this says that if it is connected, and if the set is open and closed, if a set is open and closed, then it is either empty set or K itself, okay? So K is connected. So a subset of K, if a subset of K is open and closed, then it is either empty or K itself. That's the definition of connected. So this says that closure of U is not equal to U. Because closure U, if closure of U equals U, then U is an open and closed set. So it is either empty or equal to K, but U is not equal to K, and the U is not empty, so it is a contradiction. Therefore, closure of U is not equal to U. Okay, we keep this in mind, then we continue to reason. So closure of U is not equal to U. Now, if U is in closure U, then T x lambda y, this by the definition of Tx lambda is in the line segment from X to Y. But this segment does not include Y. It includes X, but not includes Y, okay? And this segment is contained in U. This segment is contained in U by proposition 4111 on page 102. Okay. Thus, so for each Y, this is contained in U. So Tx lambda closure U is contained U. So if this is contained U, then closure U lies in the open convex set. This, okay? This is open, yeah, because U is open and this is continuous. So for continuous map, the inverse image of open set is open. So it is open. And it is convex. It's convex because U is convex. And because this map Tx lambda is a kind of linear, okay? This is a kind of linear, but it's not really linear map. Linear map, this is a translation for linear map. A linear map sends 0 to 0, okay? This one does not send 0. If you put 0 here, it does not go to 0, okay? So it is not linear, but it is close to linear. It is a translation of a linear map. That kind of map, we call it affine linear, affine map. Affine mapping. Affine mapping has the property it maps convex set to convex set. So therefore, and the inverse image of a convex set is a convex set. So this set is open and convex, okay? And it includes U. This, yeah, it is open and convex, and it contains U, and it contains the closure of U. It contains U, and it contains the closure of U. So this set is strictly larger than U, because yeah, it contains closure of U, and the closure of U is not equal to U. So this set is strictly larger than U. But the U is a maximal proper open convex set. It is maximal by maximality. If this set, it is a proper open and convex, contains one more point, then this must be the whole space K. Okay, so maximality of U implies this is not proper anymore, so it is equal to K. So we have proved the following. Tx lambda K is included in U if X is in U and lambda is from 0 to 1. So this implies that if V is in K is convex and open, then V union U is convex and open. Okay, let's understand why this V union U is convex and open. First, this V union U is open because both V and U are open. And why it is convex? To see it is convex, we take a point X, we take a segment in the set. Then there are three possibilities. The first possibility is that both endpoints are in U. Then the segment must be in U because U is convex. The second possibility, both endpoints are in V. Then the segment must be in the set because V is convex. The third possibility, the line segment has one point in U and 1 point in V. Okay. Then, okay. So then we take this, if the point is in U, we call it X. The other point, we call it Y. Then any line segment, any point on the line segment, just the Tx lambda of Y, just Tx lambda of Y. And this Tx lambda of Y, of course, is contained here. Okay, if you put Y, because yeah, Y is in point of K. So T of X lambda Y is contained here. Okay. So, but this is contained in U. So again, the line segment is contained in U. So therefore, in any of the three possibilities, the line segment, if you take 2 points in the set, the line segment connecting the 2 points still in the set. So this is convex and open. So if it is convex and open, then again, U is the maximum. So then this implies that this V union U is either U or K. So it is either U or larger than U. If it's U, then it is U. If it's larger than U, then it must be K. So it now follows from the assertion, this assertion, that K minus U is a single point. K minus U is a singleton. That means it is a set consisting of 1 point. So in fact, if you have 2 different points, A, B, in K minus U, and A not equal to B, we are going to get a contradiction. Okay, then VA, VB be disjoint open convex subsets of K such that A is in VA and B is in VB. Okay. By the assertion, VA is open and convex. By assertion, this is either equal to U or equal to K, but it's not equal to U because it has at least 1 more point A. So it must be in K. But this is a contradiction because B is not in this set. Okay, B is not in U and B is not in VA. So B is not in the union. So this is a contradiction. So this means K minus U cannot contain 2 points. So it contains only 1 point. So K minus A is equal to U. K minus U is equal to 1 point A. So K minus A is equal to U. But U is convex by our observation before the proof. If K minus A is convex, then A is an extreme point by our observation before the theorem. Since K minus this 1 point set is convex, this A must be an extreme point. Okay. So let E be defined by closed convex hull of Xk. Okay, we want to show that this contains the whole K. If not, then we prove this assertion by contradiction. Proof by contradiction. Suppose K is not equal to E, then there's a point in the complement of E. But this E is a closed and convex set. So by Hahn-Banach theorem 4313 on page 111, there is a continuous linear functional in X star, which is separate the point Y and E in this way. It separates the point Y and the set E in this way. So the real part of this inner product notation Y comma X star, this is greater than, this is greater than alpha plus epsilon. And on E, this same functional is less than alpha. So on E is less than alpha, and the point Y is greater than alpha plus epsilon. So this X star separates the point Y and E, okay? But this is an open convex set. By the definition of V, this is an open convex set. Okay, so it's an open convex set. So its intersection with K is relatively open. Since V is open, so intersect K is relatively open. It's open in K. And since V is convex, K is convex, so V intersect K is convex. So it's open, convex, and it's proper because Y, the point Y, is not in V, okay? Y is not in V because Y, this is greater than alpha plus epsilon, and this is less than alpha. So this set V does not include E, but it does not contain Y. So this is open, convex, and proper. By the definition, it is a member of U. And by what we proved earlier, any member of U is contained in the maximal element U, okay? Any member of U is contained in the maximal element U. Is contained in the maximal element U. Okay, but U, as we proved, every maximal element of U must have the form. So K minus U must equal to 1 point. Okay, and this K minus U, U must have the form K minus 1 point. And so K minus U equals this 1 point. And we proved that this is an extreme point. This is a contradiction. Why it is a contradiction? Because this V supposed to contain all extreme points. V contains E. Okay, this set contains E. And U is a maximum. U contains this set. So U contains E. So U contains all extreme points. But now, outside of U, you have one more extreme point. This is a contradiction. So therefore, this must be equal. This must be equal.